So in this lecture, I'm going to be explaining an experimental approach for understanding collapse in non-contrastive siamese network. When we use non-contrastive, it means that we are just using positive samples. We are not caring about hard, negative, and those things because our paradigm is totally different. And when we say collapse, it means either full collapse or dimensional collapse. Dimensional collapse happens when our model is restricted to a very small area and is not seeking different regions of the diverse regions of the state space, and we see that after a few iterations it collapses to just a small subspace. And the full collapse, it means that all of the things of a classifier is just all of the features are just in one very particular, very small area, which is just like a point. And so if it is a neural network, everything is converges to a constant, and so it cannot distinguish between different points. But this paper, you just explains and understands collapse through all of the claims is just through some experimental works. And this is the article of BYOL, that it is non-contrastive because it uses only positive samples. You don't have the problem of negative samples that should be big enough so that it avoids collapse, but it reduces collapse to a great extent. And SimSiam is another version, is different from BYOL, but SimSiam may collapse because they train it experimentally, and they notice that it may collapse if your model is too small relative to the data. And contrastive methods have led a recent surge in the performance of self-supervised representation learning. So methods like BYOL or SimSiam distill these contrastive methods down to their essence, removing bells and whistles, including negative samples that do not contribute to downstream performance. And these non-contrastive methods work surprisingly well without using negatives, even though the global minimum lies at trivial collapse. And they empirically analyze these non-contrastive methods and find that SimSiam is extraordinarily sensitive to dataset and the model size. And SimSiam representations undergo partial dimensional collapse if the model is too small relative to dataset size. This is the non-contrastive siamese. So the left side is given augmentation x1 and x2 of the same starting image x. SimSiam uses only the stop gradient, whereas BYOL additionally uses an exponential moving average for the second branch. And in contrast to methods like BYOL, SimSiam linear probe accuracy drops dramatically when the model is too small. So we seek to empirically understand the scenarios under which collapse occurs in these non-contrastive siamese networks and suggest potential ways to avoid it. Contrary to the previous methods that claimed that the stop gradient prediction had a high predicted learning rate are enough to prevent the collapse, we show that collapse additionally depends on the model capacity relative to the data complexity. For instance, small networks trained on large datasets are likely to collapse despite using tricks like stop gradient or batch norm on the output of the projection multi-layer perceptron. So they explore ways to prevent this collapse and find that continual layering regime, as opposed to the dominant practice of training for multiple epochs, is a promising alternative. So contrary to the previous work that claims SimSiam has no issues with collapse, they showed that SimSiam performance drops significantly when the model capacity is too small relative to the data complexity. They define a rank-based metric to measure the degree of partial dimensional collapse. The representations contain redundant information, which leads to the decline in downstream performance. Linear regression using our collapse metric and SimSiam laws can accurately predict the linear probing accuracy. This can be used to compare models without using labels or additional training time. Show that the model width is more important for downstream performance than depth, even when the total number of parameters is accounted for. Show that switching to continual learning setting eliminates collapse and restores SimSiam accuracy by as much as 80% points.